Let's start by describing a region that fundamentally makes sense in polar coordinates and is a lot harder to think about in rectangular coordinates. So we're going to use this to find the area of this pedal. And as you might remember, if we're trying, the double integral usually gives us a volume, but if we integrate the function 1 over that whole interval, then you get the same thing as doing an area. So this is just another way to do something you've probably already done before. So what I've got is the little, I forget what it's called, but you have the leaves of the functions of these types, those polar functions. Remember, if it's 3 theta, you get 3 leaves. If it's 5 theta, you get 5 leaves. And I believe if they're even numbers of theta, you get double. So like 2 gets you 4 leaves and something like that. Anyway, so we want to find the area of this thing. So we got to be kind of careful. We know that r is equal to 3 cosine 3 theta. So r is already defined in terms of theta. And that's nice because what that tells me is when I set up my integral, on this leaf, so let's say I'm only considering this leaf, no matter what, r goes from 0 out to that 3 cosine 3 theta. The trickier piece is figuring out what theta goes to. So I draw these lines just kind of like the way you think about asymptotes, or just sort of boundary lines. And it can be kind of tricky. Well, the easiest way to think about this is that cosine, well, all I know is here, it ultimately evaluates to 0. So I got to think, okay, well, if cosine of 3 theta is equal to 0, well, that then, where is cosine equal to 0? Cosine is equal to 0 when you're equal to negative pi over 2 or positive pi over 2. So that tells me that 3 theta, not theta, goes from negative pi over 2 to pi over 2, which tells me that regular theta, not 3 theta, if we divide both sides by 3, it goes from negative pi over 6 to pi over 6. And then we have to ask ourselves, okay, what are we going to integrate? Well, remember again that this is usually iterated integrals and double integrals are usually used for volume. But if we use the function that we integrate, it's just the number 1, we get essentially the area with a unit height, which it'll have the same different units, but it'll have the same magnitude as the area. So we kind of have a 1 here, and we still have our r dr d theta. And so when we integrate this, well, the antiderivative of r is just 1/2 r squared. From 0 to 3 cosine 3 theta. Which is looks like be 9/2 cosine squared 3 theta d theta. Now, this is a little bit tricky to deal with, right? So we have to use that expansion formula. Cosine squared x is 1 plus cosine 2x over 2. So whatever is x, you double it. So we already have 3 theta, so we have to double it. So that gives me 9/4, 1 plus cosine 6 theta d theta. Then we can directly integrate. Well, we'll also notice that this is an even function, right? If I plug in a negative, cosine is an even function. If I plug in a negative number and I plug in a positive number, if they have the same magnitude, they have the same output. So like cosine of +1 and cosine of -1 are the same value. So since this is a symmetric interval and this is an even function, then I can write that as doubling this, so I get 9/2, 0 to pi/6, 1 plus cosine 6 theta d theta. Now I'll take the antiderivative, 9/2 theta plus 1/6 sine of 6 theta from 0 to pi/6. But in this particular case, sine of 6 theta, if I plug in pi/6, I get sine of pi, which is 0. If I plug in 0, I get sine of 0, which is 0. So I really just get pi/6 here. So I get 9 pi over 12, 3 pi over 4, which matches my notes, so I feel pretty good about that.